Okay, we're looking at the practice exam 4, and your exam will look like this. It won't be this one, of course, but it'll look very much like it. In fact, this practice exam was somebody's exam some time ago. I have used this one as a regular exam, so you can see the level. Now, we've got a saturated solution of sodium hydroxide, contains 1.85 grams of solute in 100 milliliters of the solution. What is the molarity of the solution? So now, we've got 1.85 grams of calcium hydroxide. That's CaOH. Now you notice I didn't give you that formula. So I had to know that hydroxide was OH with a -1 charge. I had to know that calcium is in group 2 and can only take a +2 charge in order to write that formula the way I did. So even though there are some questions perhaps on nomenclature is now going to be used in working most all of the problems that we do. Okay, so we got 1.85 grams of that in 100 milliliters. Now I'm going to write milli as 10 to the -3rd. Something's under my paper. Now that's 100 milliliters, okay, written like that. Now it asks for the molarity. The molarity of the solution is the number of moles of the solute divided by the number of liters of the solution. And anytime a problem asks us to calculate the molarity, we're going to have to get these two numbers and substitute in for them to do the calculation. All right, so we got 1.85 grams of calcium hydroxide. So we got 1 calcium. Atomic weight of calcium is 40. Periodic chart is right here. Calcium is right there. So it's 40.08. We're going to have 2 hydrogens, so that's 2 times 1.008, plus 2 oxygens is 2 times 16. So what I came out with for the molar mass of this is 74.096 AMU units. Now the number of moles, that's going to be equal to the mass divided by the molecular weight. 1.85 grams divided by molar weight, that's 74.096. 1.85 divided by the answer that I just calculated. I do that all the time to keep from having to re-enter numbers. I'll do it again here in just a second. So this comes out to be 0.2496 and a whole bunch of other digits out there. Now I want to divide this by the number of liters. That was 100 times 10 minus 3. So I'm going to take my answer that I've got and divide by this number here. So I want to divide by 100 with an exponent of 3. No, it's minus 3. That would have made a mess. Okay, so we're coming out with an answer that's 0.967 and a whole bunch of digits. And if I'm checking on the exam, that's response C. Okay, let's go back so that you can see the exam, and verify we did get it right. Now, number two. Number two is what mass of uranium. So I want to know the grams of uranium in 1 milliliter. That's 1 times 10 to the minus 3 liters of 4.55 molar uranyl phosphate. Okay, so I've got some of that data, and it was UO2, and we had what, 2 of them, and PO4, and we had 3 of them, and I think that's probably all we need right there. Okay, so want the grams of uranium in this much stuff, and that's 1 milliliter. Remember now, volume times molarity is going to be equal number of moles. The volume of the solution is 1 times 10 to the minus third times the molarity is 4.55. Now that's going to be moles of this compound. So that's moles. Now, the question asked me for the grams. I'm sorry? Okay, I thought someone was asking a question. Okay, so the grams of uranium, I want 1 mole of the compound. And 1 mole of this compound, if you look back up here, it's got 2 uranyls in it. So it's got 2 times 1, 2 uraniums. And uranium on the atomic, on the periodic chart is down here. It's 238.08 is the atomic mass of uranium. So it's 238.08 grams. So if I've done my math correctly, I should have my answer. The question was grams of uranium. So let's do that. We get 1 with an exponent of minus 3. I want to multiply that by 4.55. Then I want to multiply it by 2 and multiply it by 238.08 and divide by 1. No, I can even do that in my head. Okay. But I'm looking at some numbers that don't look right to me. Okay, well, let's see what we've got. 1 times 10 minus 3. Molecular weight is 4. Molarity of the solution is 4.55. And then that'll be the number of moles. Divide that. One mole would have that much in it. So let's do the math again, but I don't see where the mistake is. Okay, and then times 2 times 238.08. I'm still getting 2.16 grams. Okay, I'm getting 2.166 and digits like that in grams, and the answers are all given in milligrams, so I think there's a mistake here. I want to go from grams to milligrams, and milli is 10 to the minus third. So 10 to the minus third grams is 10 to the minus third grams, that's right. So I'll have to divide that by 1 times 10 minus 3. And I'm getting 2.166. 665 something, I'll say 2167 milligrams. Okay, so that's what I'm getting for an answer. I'm getting something half as much, but I count that? No.
There were 3 UO2s.
I'm sorry. Oh,
In the
thank you
original
so
problem,
much. I
there were
copied.
3 UO2s.
Thank you. It's 3 of these instead of 2. So I need to, this should have been a 3. Okay. And so if I divide this answer by 2 and multiply it by 3, that ought to get the same answer. Divide by 2 and multiply by 3. Now that looks better. Yes, thank you. I'm all the time doing silly things like that. I copied that second digit twice. So the correct answer was supposed to be 3249 and 792, and the 3250 is the closest to 3 significant figures. Okay. Yes. Any of you catch me copying stuff down wrong, I appreciate you tell me that. I do these things all the time. I have been known to make a mistake, maybe more than once. Okay, it's moving right along. We're doing number 3, and you can read along with me as I copy the data down that we'll need. Number 3, we have a stock solution of perchloric acid is 75. Now, perchloric acid, I got to know that if it's perchloric, it's made from perchlorate ion. So perchlorate is ClO4 and has a -1 charge. So perchloric acid is going to be HClO4. Okay, so it's 75.5% perchloric acid, and the density is 1.67 grams per milliliter. Okay, let's get that over so you can see my pad a little better. Okay, so there is the data. It wants to know what is the molarity. So again, it's asking for molarity. So that means I've got to have number of moles, and I have to divide that by the number of liters. Now, it doesn't matter what the two numbers are. I'm going to have to divide them out. So you know what I'm going to do? I'm going to make this denominator 1 so that I can divide that. I mean, even I can do that without making a mistake. Okay, to divide by 1. Okay, so if I had 1 liter, okay, that would be 1,000 milliliters. And I went to that because I'm looking at the density over here, it's in milliliters. So if I want to convert that, that's going to be 1.67 grams in 1 milliliter of the solution. So multiply that out, and I'm going to come up with 1,670 grams of the solution. So I can't put that, I can't convert that to moles up here because this is solution. It's got water in it too. I want to know just how much phosphoric acid in it. Well, the percentage tells me that answer. There's 70 for 100 grams of that solution. It would have 75.5 grams of the acid. That's going to cancel. So I'm going to take that answer, multiply it by 75.5, and divide it by 100. And that tells me that I have in that solution 1260.85 grams of the perchloric acid. Now all I have to do is get the number of moles. Well, I want to convert grams to moles for perchloric acid. And I'm looking at my formula. It's got one hydrogen, so I'm going to take 1.008, that's the hydrogen mass, plus chlorine. Chlorine off the periodic chart, 35.45 plus, and it's got 4 oxygens, and that's 4 times 16 for oxygen, 16.00. So that comes out to be 100.458 in 1 mole. So I want to take this answer and divide it by what I've got on my screen. So I've got 1260.85 divided by my answer, and I come up with 12.55 and some other digits moles. So the molarity is going to be 12.55 divided by 1. That many moles in 1 liter. So 12.55 should be our correct answer. So let's go over here and let you see this practice exam again. And we get 12.6 is correct. All right. Let's go to number 4 while we're here. Now, we've got a reaction. It's C3H8. There's 3 of them. That's propane. And 20 chromic acids from chromate ion makes 9 carbon dioxides, 10 chromium-3 oxides, and 32 waters. We want the mass of chromium-3 oxide that would form from 1.5 grams of propane and 35 milliliters of 6.26 molar chromic acid. So the 3 things involved in my reaction are the propane, C3H8, and the chromic acids. There's 20 of those. And we're going to make 10 chromium-3 oxide. Okay, let's get over here so you can see the pad a little bit better. All right, so I've got it set up. There's the 3 propanes and 20 chromic acids to 10 chromium-3 oxides. That's what's in the problem. Problem says we have 1.5 grams of this. Now, if this is in grams, I want to express the balanced equation in grams. So that's going to be 3 times the molar mass of the compound is given up on the problem at 44.09. Now, this solution was 35 milliliters of 6.25. So I'm going to write that as 35 times 10 to the minus 3, 35 milliliters multiplied by molarity. Molarity was 6.26. That'll be moles. The equation is showing 20 moles. So I'll write that down here. Now it wants to know how many grams of this, what mass. Okay, the equation is showing 10 moles, and the mass of a mole from the equation was 152. See, now working the problems like this, I've got everything set up so it's really easy. What I've got here is this number divided by this one is my rebalancing factor based on propane. This divided by this is the rebalancing factor based on chromic acid. So I'll have 2 rebalancing factors. Let's calculate what they would be. I've got 1.5 divided by 3 and divided by 44.09. So I'll write it down. I would normally just keep this on my screen. 0.01134 and some other digits. It's important, don't round off rebalancing factors. Like I said, I'll keep it on the screen and reuse it rather than try to recopy it. You saw what I'm doing, I copy things down. Okay, so 35 second exponent negative 3, that's 35 milliliters times 6.26. That's going to be moles. I want to divide it by 20. Rebalancing factor on this one is 0.01095. But the important thing is this one is smaller than this one. So this is the limiting reagent. So my answer is going to be this rebalancing factor times what I've got under this question mark up here in the problem. So my answer is my RBF. And when I told you about writing these things down, I wrote them down so you could see that this one was smaller than this one. If I had been doing it on my calculator without writing a step down, I could have looked up on my screen and compared the two numbers. I've still got the 0.01134 on the screen, and I've still got the one I just calculated. So the one I just calculated is the one I want, and I need to multiply that by 10 times 152. So times 10 times 152 gives me 16.6516 grams of the Cr2O3. Okay, and if we look at the answers, okay, that would be C. 16.7 is the correct answer for you. Okay, so this particular problem did combine mass and volume and molarity in the same problem. Okay, let's do number 5. All right, so number 5. Okay, number 5. Same reaction. How many moles of product will form from 2.5 grams of propane with 75 milliliters of 5.33 molar chromic acid? Well, that's very much like the previous one, except we're going to do moles of product as the answer. So what I'm going to do is it would really help if you guys would bring a copy of the practice exam so you can follow along. It would save us a lot of time having to jump back and forth like this. But okay, we've got 2.5 grams of propane. The propane was 3C3H8. H8. Let's do it again. 2.5 grams, and it's 3C3H8. The equation is showing 3 times 44.09 grams of the propane. That's reacted with 20 H2CrO4s. The amount that's given in the problem is 75 times 10 minus 3. And it's the 75 times 10 minus 3, the molarity is 5.33. And that will be moles. The equation is showing 20 moles. So again, we're going to have two rebalancing factors. But now, in order to get moles of product, all I'm going to do is just add the number of moles that are there. So I've got 9 plus 10 plus 32 moles of product. And so we want to know how many will we get from the problem. All right, here's my two rebalancing factors. So let's do the rebalancing factors. So I've got 2.5 divided by 3 and divided by 44.09. Okay. This first rebalancing factor I'm getting to be 0.0189 and some other digits. 75 with an exponent of minus 3 times 5.33 divided by 20. I get 0.01998 and some other digits. Now I see this is going to be my rebalancing factor. Glad it came out that way. I want to show you what I would do. I'm not going to copy that number back. First of all, it's been rounded off. Second of all, I might transpose the 1 and the 8 or the 9 and the 8 when I try to do the numbers. I don't do that. But I'm going to put this data back in. I'm just going to say 2.5 divided by 3 and divided by 44.09. And I've got my number back on the screen, 0.01890073333, etc. Now, I want to multiply that by what's over there. So my answer is going to be the rebalancing factor again, multiplied by what's under my question mark. It's a 9 plus 10 plus 32. And I'm going to write it just like that. So I'm going to say times, so I didn't have to re-enter that number, times a left parenthesis, 9 plus 10 plus 32. Okay, so I'm coming out with 0.9639 and a whole other bunch of digits of total moles. You see, I didn't work that. Work through with this one and get the amount of the first one. And then work through with this one, get the amount of the next one. And work through this one, get the amount of the next one. Add them all up. See which one's smaller. Work through this one and calculate the first one. Work through this one, calculate the second one. Work through this one, calculate the third one. Add them all up. See which one of those are smaller. And can you believe how long that would take? Where you saw how long it took. And it would take a lot less time, believe me, if I weren't explaining it. I could do all of that really right on my calculator. All right, so let's go look at the next one and see that we did it okay. Get this one right, get the next one. Yeah, 0.964 is the correct answer. Now, number 6 is a yield problem. It's good because I want to show you what I think is the best way to handle problems like that. We're going to deal with that yield part last. Okay, so what volume of 6.25 molar of chromic acid will form 1.5 grams of the chromium-3 oxide? So I've got the two things involved in the reaction are the chromic acid and the chromium-3 oxide. And we want 1.5 grams of this. The equation is showing 10 times 152 grams of that. And it wants to know how much of this. It said volume. I'm going to first calculate moles, because volume times molarity is equal to moles. If I know the moles and the molarity, I'll get the volume. The equation is showing 20 moles. So my number of moles, that's going to be my rebalancing factor, which is this number divided by this one. It's 1.50 divided by 10 and divided by 152. And then I need to multiply that. That's the rebalancing factor times what's under my question mark is 20. And my answer units are going to be moles. Wouldn't it be nice if you had a calculator that would give you the units of the answer? Someday they probably will have, but not yet. Okay, so this number comes out to be 9.868 times 10 to the negative 4, but I want to multiply it by 20. And what I'm coming out with now is 0.0099868 and a bunch of other digits, moles. That's equal to the volume, which I don't know, times the molarity, which I do. And the molarity for number 6 is 6.25 molar. So if I take the number I've got on my screen and divide it by 6.25, I'm coming out with volume is 0.0015. Oh, I never did turn it where you could watch me. Let's do that. Okay, well, here's where I am with the setup. 0.00157 and a whole bunch of other digits here. Liters. Now look at my answers. My answers are in milliliters, so I need to convert from liters to milliliters. So liter and milliliter. Milli is 10 to the minus 3, so I need a 10 to the minus 3 in the denominator. 10 to the minus 3 liters and 10 to the minus 3 liters is 1. Okay, so divide that now by, divide it by 1 with an exponent of minus third. So I come up with the volume is equal to 1.57 and some digits milliliters. But we're not done yet. Don't look at the answer. Well, I really screwed up. I should have given you that answer as one of the wrong answers, but I didn't. Okay. And the reason why that's not the correct answer is we assumed everything was 100% yield up till now. But we know we're only going to get 68.6% of what we expected to get. So I need to scale, this is the amount of a reactant. So I need to scale that up by that 68.6%, which means I need to divide this by 0.686. That's the fraction of, that is that percentage. So if I take that answer and divide it by 0.686, now that should be the answer. And somewhere, have I done it again? Okay, what if you got 6.25 molar, I have 1.5 grams of this. equation showing 10 times 152, I believe, and that's correct. Balance is 20 moles, so I'm going to take that, multiply it by 20. So I think that 1 point. I'm sorry? Okay, let's try again. 1.5 divided by 10 divided by 152. And that looks like, oh, I've got a decimal point off when I wrote it down there, I think. But 1.5 divided by 10 divided by 152. That looks right. Then times 20. Okay, so I've got this number. And now I need to divide that by 6.25. Divided by 6.25. And I get this number, which is not that number there. So I did do some stuff bad on the calculator a while ago, I think. Okay, so that gives me that. I want to divide that by 1 with an exponent of minus third. And I get that number. And yeah, that's 3.15 something or other. And then I need divide that by the percentage. Percentage was divide that by 0.68686. Yes. And now that looks a little bit better. The setup was correct. I just copied some numbers down wrong. The answer is 0. No, it's 4.6033 milliliters. That's how much I would have to use in order to get actually 1.5 grams if the reaction is only 68.6%. So that's, if I'm looking at a problem like this where I need to scale up a reactant because the reaction isn't 100%, then I'm going to take the answer that I get, assuming that it is, and divide it by that fractional equivalent to make the amount I start with more, because I'm only going to get 68% of the amount of product I think I'm going to get. If it had been what would be the yield if I've reacted this much, so many milliliters of chromic acid to get my product, then, and it was only 68%, I would calculate the amount that I expected to get and then multiply it by 0.686 if it's the product. So you have to figure out which way to use the percentage, whether you're scaling up because the reaction isn't efficient and you want to make a certain fixed amount of product, or if I know that it's only 68.6% and I want to know how much of a product I get, I'll calculate the amount as if it were 100 and then multiply it by 0.686. Okay. All right, let's go back to here and go to the next one. Be number 7. Okay, and number 7, we're going to get the amount of CO2 at some temperature and pressure for 1.5 grams of propane. So I've got 3 C3H8, and I've got 1.5 grams of that. And the equation is showing 3 times 44.09. grams of propane. Now I'm going to make carbon dioxide. In this case, I've got 9 CO2s. And we want to know an amount of CO2. And so what I'm going to do is calculate moles, because I know that PV equals nRT. So the equation is showing 9 moles. Now let me pull that down and let you see the pad again. So I've got this set up, 1.5 grams of propane. The equation is showing 3 times 44 grams. It's showing 9 moles of CO2. So I'm going to calculate the moles of CO2 because I know that P times V equals nRT. So I can calculate the volume of the CO2 at some temperature and pressure once I know the number of moles. So I'm going to calculate the number of moles using my regular method. There's my rebalancing factor. That's equal to 1.5 divided by 3 times 44.08. And my answer in moles is going to be the RBF times what's under my question mark is 9 moles. Okay, so let's do that math. I set it up this way so you can see I can string that all together in one calculation. 1.5 divided by 3 and divided by 44.08. No, 9. I wrote 8 there. It's 9. Okay, and then I want to multiply that by 9. So what I'm coming out for number of moles is 0.1020 and a whole bunch of digits. I don't want to round this off. I'm going to say the problem wanted to know what volume. So volume is going to be equal to nRT divided by P. Now the N that I have here is the answer I just calculated. So I don't have to re-enter that on my calculator. The R is, so that's my answer from up there. Its R is 0.0821 liter atmospheres per mole per Kelvin. The temperature is 25 degrees. That's 298.15 if you want it. Kelvins. And the pressure in the problem, the pressure was 735. So the pressure is 735 divided by 760 to get it into atmospheres, to have all my units consistent. So let's do the math. See, I've still got my answer on my screen. So I'm just going to say times 0.0821 times 298.15 divided by, I'll put it in like that, left parenthesis, 735 divided by 760, close my parenthesis. That should be good. So I'm coming out with a volume of 2.58 and a whole bunch of digits, liters. And I think that's close enough. The answer is given in liters. Oh, I know. I put 298.15, so it's caused me instead of 298, which I might have used in the earlier version of it when I worked this out. But the correct answer is this one. And 2.57, I've always told you the answer should be plus or minus 1 in the least significant digit. So that still fits. So it should be okay. All right, let's see for number 8. We're not going to finish all of this, obviously, in the next 6 minutes. So probably what I'll do is go ahead and end this recording, and then either Friday or outside of class, I'll work through the other problems on this exam. So you'll have them before then. And the videos are all up now. I've taken down the old videos that I had up there, and I've linked them all to the same video files that I've uploaded to YouTube. It'll load faster and take up less storage on D2L. So we're okay. All right, number 8. What volume of propane gas at some temperature and pressure will react with, 75 milliliters of 3.5 molar? So I've got 3 C3H8, and it reacts with 20 H2CrO4s. And we want to know how many liters at some T and P we would get if I'm reacting 75 milliliters of 75 times 10 to the minus 3 liters. Molarity of the solution is 3.25. Equation is showing 20 moles. All right, so let's stop that and let you see. I've got it set up here on the pad. How many liters at some temperature and pressure of propane reacts with 75 milliliters of 3.25 molar. The equation is showing 20 moles. Okay. All right, so there's my rebalancing factor. Again, we're going to work this in terms of moles. How many moles would that be? And the equation is showing 3 moles. So my answer in moles is going to be 75 times 10 minus 3 times 3.25 divided by 20, and then times the number of moles shown in the problem is 3. Okay? That's going to be the number of moles in my ideal gas equation. So I get 75 with an exponent of minus 3 times 3.25 divided by 20 is that number, multiplied by 3 is that number. So my answer here, N, I don't need to write it down, but I will for your sake, it's 0.0365. And a bunch of other digits. And then I'm going to use volume equals N, that's my answer, times R, 0.0821. Temperature in this problem is 290. Did I work? Oh no, I better look back again. Number 8, 75 milliliters, that's correct. And I want the volume of that. Okay, that's going to be number of moles. I've got it set up right so far. And the temperature is 298. So that's nRT over the P, and the pressure is 735 divided by 760. So it's the same type of problem we had a while ago, really. So I've got my answer, times 0.0821 times 298 divided by, left parenthesis is 735 divided by 760, close the parenthesis. If you want to do it that way, be sure to put those parentheses in, okay? So I'm coming out with 0.92, 0.92495, whole bunch of digits, liters, seeing my answers in milliliters. So I want to go from liters to milliliters. Milli is 10 to the minus 3. And then I want to divide this answer by 10 to the minus 3. Divide by 1 with an exponent of minus 3. I get 924.96. So that should be the answer. Okay, so let's go up there and do the screen share so I can show it to you. Do this one. So there we are. 924.9 is 925. That's right. Okay, so we're good. Okay, now I understand if any of you guys have to leave, I'm going to work at least through about half of the questions while I'm on this video. And if you have to go, that's okay. But I will upload it as soon as I get it converted and put it on YouTube. I'll upload it to D2L so you guys can come back and pick it up later if you need to. And then I'll finish it up either Friday or some other time if we need more time on Friday for this. Okay, so number 9 is where we are now. And we've got a balloon has an inflated volume of 5 liters. What mass of helium is required to fill the balloon at 25 degrees C in 1 atmosphere? So that's just a PV equals nRT problem. Okay, so let's stop screen share and go down and we'll work it here on the pad. Okay, so, okay, we want the mass of helium. So if I'm asking for mass, I'm going to first solve for moles then. So the number of moles is going to be equal to P times V over R and T. So the pressure that we have in this balloon is 1 atmosphere. That's a good number, like that number. The volume that we have is 5 liters. That's a good number too. R is 0.0821 liter atmospheres per mole per Kelvin. Temperature in kelvins is 298 also. Okay, so I can do the number of moles. That'll be easy enough. So 5 divided by 0.0821 and divided by 298 is, the number of moles is going to be 0.204 and some digits. So this is moles of helium. That's like 2044 essentially. With some other digits, that's how many moles. The equation was mass, so this is moles. So if I want to go from moles of helium, one mole of helium from the periodic table is, helium is 4.00 grams per mole. Okay, so I just need to multiply my answer by 4. And I'm coming out with 0.81746, some digits. Okay, and if we go back and look at the problem, I think that's okay. Again, that's within one number in the last significant digit, so that's okay. All right, and number 10. Okay, number 10 is calculate the number of dichlorine molecules in 5 liters container at 40 degrees C and a pressure in terms of kilopascals. And I gave you the conversion factor between kilopascals and torr or atmospheres. 1 atmosphere is 760 torr as well. So number of molecules of dichlorine. So I'm going to get number of moles first. That's going to be P times V over R and T. The pressure that we want is 2.14 times 10 to the 4th pascals. Now I've got to convert that to get to atmospheres. So I want to go from pascals to atmospheres. Now, I'm given at 101.3 kilopascals, so the pressure is 101.3 times 10 to the 3rd, 101.3 kilopascals for 1 atmosphere. So I need to divide this number that I have on my, no, I don't have it on my screen yet. I guess I could go ahead and do that. 2.14 exponent 4 I want to divide that by 101.3 exponent 3rd. Now that gets me into atmospheres. What I have on my screen now for atmospheres is what I have on my screen now is 0.21125 atmospheres. I want to multiply that by the volume, and the volume is 5 milliliters, so I want to multiply that by 5 with an exponent of -3 because it's got to be in liters and it's milliliters in the problem. So that gives me the number of milliliters. It's at 40 degrees C, so I want to divide by R, divide by 0.0821, and divide by the temperature. The temperature is 40 Celsius, so I add 273, so it's 40 plus 273. And when I'm done with that, I come up with a fairly small number of moles. So I'm coming up with 4.11 times 10 to the -5th moles of Cl2. But the problem wanted molecules. So if I want to go from moles of Cl2 to molecules of Cl2. Well, 1 mole is Avogadro's number, 6.02 times 10 to the 23rd. So I need to multiply that number that I got times 6.02 with an exponent of 23. So what I came out with now, the number of molecules is 2.47 in digits times 10 to the 19 molecules. That's a reasonable number. I'm getting something slightly different from what's shown on the problem. The problem is showing 2.6. So that's off by a little more than the 1 unit. Well, 2.5. No, it's not. 2.6 versus 2.5. That's still plus or minus 1 in that 1 decimal place. So that's acceptable. All right, so let's go back and get the next one. Ready to do number 11 now. Let's see. All right, I've got a mixture of gases. It's got 5 moles of nitrogen. Nitrogen is N2 if I need it. And I'm mixing that with 8 moles of oxygen. Oxygen is O2, so if I need it. And the total pressure is equal to 760 torr. Okay, you can't see what I'm doing. So stop that. Now, So there we go. And now we want to know what's the partial pressure of nitrogen. So the pressure of nitrogen in the container by Rayleigh law is the mole fraction of the nitrogen times the total pressure. Okay, so I know the total pressure. Total pressure is 760 torr. Let's get the mole fraction of the nitrogen. The mole fraction of nitrogen, that's going to be the moles of nitrogen is 5, divided by the total number of moles, 5 plus 8. So my pressure due to nitrogen is going to be this number times 760. So let's just do that all in one swoop. So 5 divided by a left parenthesis, 5 plus 8, close the parenthesis. That's the mole fraction. That's 0.3846 times 760. That's 292.3. torr. Okay, so if we go back and take a look. There we are. 292 is correct. 212. Okay. Now this is going to be a Graham's law problem. See the hints already. It's found by an experiment that it takes oxygen 5 seconds to diffuse 35 centimeters. How long will it take for sulfur dioxide to diffuse the same 35 centimeters at the same temperature and pressure? Now, Graham's law says the velocity of gas 2 divided by the velocity of gas 1 would be the square root of molecular weight of gas 1 divided by molecular weight of gas 2. The velocity is inversely proportional to the square root of the molecular weight, inversely proportional. So label number 2 is in the numerator of velocity, but it's in the denominator of the under the radical. Okay, so let's put in the numbers and see what we can get. The velocity, it takes oxygen, so let's say the velocity of oxygen, I'll make oxygen equal to number 2, and sulfur dioxide, yes, SO2 is going to be number 1. All right, so I can put in the molecular weight. So number 1's molecular weight is sulfur and 2 oxygens. That's sulfur is 32.06, I think. 32.07. And it's got 2 oxygens, so that's 2 times 16. So all right. And for the oxygen is number 2. Oxygen, it's 2 times 32, O2. So I've got 2 times 16. I did it in my head while I was writing it down. Okay, so there 2 times 16, 32.07 plus 2 times 16 up there. So let's do the math to get that other side. All right, so we got 32.07 plus 2 times 16. That's 64.07. And divide by, that's going to be a 32. And now I get, this actually comes out to be almost exactly 2. So I want to take the square root of that. And so I've got the velocity of the O2 divided by the velocity of the SO2 comes out to be 1.415 essentially. There's a whole bunch of digits out here. Now let's put in what we know and solve for what we don't know. What we know is it takes 5 seconds for oxygen to diffuse 35 centimeters. So velocity of O2 is 35 centimeters in 5 seconds, centimeters per second. That's going to come out 7. So the velocity of the SO2 then is going to be, I've got my 7 up here, so it's going to be 7 divided by my answer from over there at 1.415. So that's going to be the velocity of the SO2. It's going to be 7 divided by the answer that I still have on my screen, so I don't round off anything. I'll come out to be 4.947 centimeters per second. All right, so there's my velocity, and I want to know how long. So velocity is distance over time. So the velocity, I want to go 35 centimeters. And the velocity that I'm using is the 4.947 digits centimeters in 1 second. There's my conversion. So I need to take the 35 centimeters and divide by the answer I've got. 35 divided by that answer gives me 7.07 centimeters. So the time for the SO2 is 7.07 seconds. Now before we look at our answer, let's see, does this make sense? SO2 is heavier than oxygen. It ought to travel slower. So if it takes 5 seconds for oxygen to travel 32 centimeters, something heavier would take more. So sure enough, that does come out fitting right. It may not be correct, but it seems to fit the expected answer anyhow. So yes, it turns out that is the answer, number 7. Okay. I'm moving right along. Now we're doing van der Waals gases. Van der Waals equation to get the pressure exerted by 24.5 grams of ammonia, here's its constants, confined to 2.15 liter container at 300 degrees Celsius. I think I better start a fresh new page on that one. That's a big problem to work. Okay. All right. We're doing number 13. The van der Waals equation is P plus A times N squared over V squared, all multiplied by B minus NB equals NRT. Now, the first thing I'm going to do is I'm going to see which of the 2 possible things I could solve for is being asked in this problem. I can ask you to solve for pressure, and I can ask you to solve for temperature, because either one of those is a simple solution. Volume is a cubic equation, and I'm not going to give you that difficult a problem. If you've got a good equation solver on your calculator, it wouldn't matter. But we're going to do just the either T or P. This one asks for P. So let's solve for the pressure. I want to divide both sides. Let me let you see what I'm doing. Okay, so I want to divide both sides through by V minus NB. So divide by V minus NB and divide over here by V minus NB. When I do that, those pieces are gone. Now, I'll just have P plus AN squared over V squared. Well, now I'm going to subtract AN squared over V squared from both sides. And then this will cancel this, and I'll have P by itself. P is going to be equal to then nRT divided by V minus NB minus A N squared over V squared. So there is my setup. Now, my A constant is 4.3044. My B constant for ammonia is 0.03747. And my volume is going to be 2.15 liters. My temperature is going to be 300 Celsius, so that's 300 plus 273.15 if we needed it. And my N is the number of grams is 24.5 divided by the molecular weight of ammonia. You have to know ammonia is NH3. So it's 1401 plus 3 times 1.008. So it's 14.01. 3 times 1.008. I get the molecular weight is 17.034. All right. So now I'm going to be following this equation right here on my calculator. And I'm not going to do each one of these little steps one at a time and write down numbers and do all the math. I'm going to divide this out first. And if I take this 24.5 was the mass, right? Divided by the molecular weight I just calculated. So my N is 1.438 and a whole bunch of digits. But I'm just going to say that's the answer that's on my computer screen. So everywhere I've got an N, I'm going to take that N and I'm going to put it right there. And I'm going to put it right there. And I'm going to put it right there. Okay, so now let's just take this and do it on the calculator. What I see, N. So that's my N. I want to multiply it. So I'm going to say times. My computer put answer in there. Times. R is 0.0821 liter atmospheres per mole per Kelvin. Times the temperature. The temperature is, left parenthesis, 300 plus 273.15. I'm going to put it in. Close the parenthesis. Now I've got nRT on my screen. I want to do divide. I want a left parenthesis. I want volume is 2.15. Minus, the answer is still on my screen, second answer, times B, 0.037847. Close my parenthesis. I've got it closed. Now I want to do minus. So I do minus my answer squared. Second answer squared. Divided by V squared, 2.15 squared. Now, if I haven't screwed up somewhere, when I push the enter, my calculator should give me the answer to the problem. Okay, so my answer comes out to be 31.849. My pressure is 31.849, other digits. That's what I was solving for. But what were the units? It's atmospheres. So I happily go over and look at my answers, and lo and behold, they're in pascals. So I've got to convert from atmospheres to pascals. Now, let's look on I was given that 101.3 times 10 to the third, 101.3 kilopascals is 1 atmosphere, 760 torr. So I want to multiply that by 101.3 times 10 to the third times 101.3 with an exponent of 3. And I'm coming up with the pressure I'm coming up with is 3.2 3.23 times 10 to the 1, 2, 3, 4, 5, 6, 10 to the 6 pascals. Well, I'm a little bit off, but I think I may have again entered some of these numbers just off a little bit. You can double check this and see whether you get the 3.23 times 10 to the 6 or the 3.08 times 10 to the 6 is what's shown in the problem. But I think it's kind of funny. We're in between. No, we're not. 3.23. It's actually closer to this number the way I've got it. So these numbers are pretty tight. I think I'd need to work it again. If I were you, came out with answers like that, I'd do it over again. But right now, the math that I showed you is correct. I've entered a digit wrong somewhere in the calculator when I did the math. But I don't want to take the time right now to worry about that. Okay, so let's do number 14. Number 14, what would be the pressure if 24.5 grams of ammonia were confined to 2.5 liter container if the ammonia were an ideal gas? Well, PV equals nRT. That's the relationship we're going to have to use. We've got 24.5 grams of ammonia. The volume of the container is 2.15 liters. And you know, I need a little more data there. I need to know the temperature of the gas. So I'm going to assume maybe it was 298. Let's try that. Temperature 298 Kelvin would be 25 degrees C. But I think I can't do that problem without that data. So let's fix this. Okay. Now, we want to know what would be the pressure. So pressure would be equal to the number of moles is 24.5 grams divided by the molar mass. We calculated a while ago, 17.03. And that's the number of moles. R is 0.0821. And the temperature we're going to say is 298 until we know differently. Let's see what we get as an answer. And that might tell us whether that's the right temperature or not. 24.5 divided by 17.03. That's the number of moles times 0.0821. And nRT times 298.15. I'll put that in. Okay, so I'm coming out with pressure is 35.215 atmospheres. We still have to do the same conversion because the answer is in Pascal. So I want to change from 1 atmosphere is 101.3 times 10 to the third pascals. Okay, so times 101.3 exponent 3. And I'm coming out, yeah, the temperature couldn't be that temperature. I'm coming out with a different temperature too. So, I'm sorry, different pressure. I'm coming up with 1, 2, 3, 4, 5, 6. I'm coming up with 3.57 times 10 to the 6 pascals. And it's saying 3.19 times 10 to the 6. So again, I don't know what the temperature was. I can go back and fix that. So I need to star that one and the one that I just worked. And I'll take care of that offline. Okay, we'll do one more and then we will stop for the day. Okay, we were close, but not, no cigars, but the temperature must have been pretty close to 25. Okay. All right. When a certain process is carried out in a sealed container, the heat flow is minus 50.6 joules. When the same pressure process is carried out in a constant pressure of 1.25 atmospheres, the heat flow is this. What's the value of Q at constant pressure? Okay. When the process is carried out in a rigid container, that would be Q at constant volume, we get minus 50.6 joules. When the process is carried out in Q at constant pressure, 1.25 atmospheres, the heat flow is minus 72.2 joules. That's kind of an easy problem because the answer is given in the problem. It said what would be the value of Q at constant pressure. Well, it told you if you carried it out at constant pressure, it's 72.2 joules. So that's the answer. The little thing that was sort of added in was it was at a constant pressure of 1.25 atmospheres. You know, it really does not matter at all what the pressure is. What matters at all is that the pressure is constant. So number 15, the correct answer is obvious D, because it's given in the, I guess the others look very much like this, so maybe I should go on and do another couple of these till I run out of this stuff. Okay, again, good. Same data, we want the value of the work at constant pressure. Okay, we do have to work a little for this one. The relationship between heat flow and all of this is delta E is equal to Q at constant volume, and delta H is equal to delta E plus delta PV. Let me get this where you can see my pad again. And work is minus P delta V. So P times delta V is minus, so delta H is equal to delta E plus P delta V, and P times delta V is equal minus work. So this is minus the work. So delta H is equal to delta E minus the work. And we want to calculate work. Work then is going to be equal to delta E minus delta H. Now, I'm given a problem that when we're at constant volume, Q at constant volume is delta E. So that's minus 50.6 minus the delta H value is the Q at constant pressure. That was minus 72.2. So this times this minus is plus. So I'm going to take this number and subtract 50.6. So 72.2 minus 50.6 should give us plus 21.6. Work is plus 21.6 joules. And that is the answer that we have on the problem. And let's do number 17. What's the value of delta E for the process? Well, this one is certainly easy again because it's given in the problem. If you carry out a process in a sealed, rigid container, the volume is going to be constant. The heat flow at constant volume is delta E. So delta E is minus 50.6. That's the answer to that problem. Number 18. What's the value of delta H for this process? Well, we've already said that. That's going to be the heat flow at constant pressure. It's minus 72.2. Okay, let's kind of stop right here, and we will pick up here in a later video, or we will do it on Friday, one or the other.